We've been talking about enolates. So we get enolates by deprotonating a ketone, aldehyde, ester, etc. So here I've got a ketone, I treat a ketone with some base, I take a proton from this carbon, I get this enolate. Now earlier when we talked about enolate alkylation, especially with plain old ketones, I said that we need a really strong base like LDA to make sure that we fully deprotonate it, that 100% of this goes to that. What if we don't do that, right? So what if I give it a relatively weak base, let's say like sodium methoxide or something, where only a little bit of enolate is formed? Well, what happens then? In that scenario, I've got a little bit of enolate and I've got a lot of ketone. So I've got some nucleophile and some electrophile together. So here's my nucleophile that can now attack some of the electrophile that's still in the pot. Again, they're coexisting. So what do these arrows give me? Try to draw it yourself. This is what I get when that makes a new carbon-carbon bond. And again, I like carbon-carbon bonds. I like them a lot. Here it is. There's my new carbon-carbon bond, right? Between the enolate carbon here and the carbonyl carbon here. So this is called a dimerization because two molecules, dimer, are coming together. This is going to then take some stray proton, probably one of the ones that our weak base took, and here I am. I'm at what's called a beta hydroxy ketone. So in terms of pattern matching, right? Whenever I see alcohol 2 carbons away from that carbonyl, I think about this kind of reaction where an enolate attacks an alcohol, or an enolate attacks a ketone. So to summarize, I am converting some but not all of my ketone into an enolate. When I do, now I've got enolate, which is a really good nucleophile, and a lot of electrophile around. And in that case, the two can react, right? So the electrophile that we spent a few weeks on reacts with the nucleophile we spent last week on to make this new carbon-carbon bond, which will bring us to this thing, which is called an aldol product. It's less common, but the aldol reaction can also be acid catalyzed as well, and basically goes through the same mechanism. The difference is that now, instead of an enolate nucleophile, now I'm counting on my enol nucleophile. Okay, so this is going to be my nucleophile. It's a weaker nucleophile than before, but the acid catalyst will make my electrophile more electrophilic. Here you go. Here's my nucleophile. It's a weak nucleophile, but here's my electrophile. It's now a really strong electrophile. So I'm making the same bond I did before, this carbon to that carbon. Here's my product with that extra proton, which will then get taken back by the acid. Again, I just have catalytic acid, so there's not enough to go around. So after it loses that acid proton to the solvent probably, I'm going to end up with the same product. So I can do this aldol chemistry either under base or under acid catalysis. These aldol products can dehydrate, which is to say that they lose water, going from this alcohol to this conjugated enone, right? Conjugated double bonds here and there. This is a really common thing. It can happen in acid or base. So thinking about how the acidic mechanism works, here I've drawn the enol form of this, and if I have an enol form and a protonated alcohol over here, now this is a leaving group, and I can push electrons all the way from my enol oxygen all the way down to expel water. Again, dehydrate, right? Get water away. So if we do an acid catalyzed aldol like this, it's very easy for it to keep going to get this dehydrated product, particularly when we'll end up with a highly substituted double bond like this. Much the same mechanism happens in base. So in base, even a relatively weak base will give us a tiny bit of this enolate. As soon as we form this enolate, now this OH is a reasonable leaving group, right? Just like it would have been if it were on this carbon. So I'm pushing electrons down, down, down. I kick out hydroxide here, and I get to the same product. You might look at this and say, what kind of elimination is this? This is an elimination reaction. Should I think about this as E1 or E2, right? So E1 goes through a cation. This doesn't go through a cation. E2 is a one-step reaction. This is two steps. And so this is neither E1 nor E2. This is a different reaction. This is called elimination through conjugate base, E1CB. Two-step reaction. The first step is the slow step. Making the enolate is the slow step. And then as soon as the enolate is made, then it can kick out the leaving group in a second fast step. So it's two-step reaction, E1CB, different from E1 or E2. Both of these are products of aldol reactions. Take a second here, stop the video, and see if you can figure out from which starting materials these aldols come from. For this one, we want to focus on the new bond that's being formed. And that new bond that's formed is going to be right there between the two carbons there. So we have a new alcohol as our product. Here's the new bond that's formed. It's formed between this enolate and this carbonyl compound, and obviously we would just get that enolate. So it's an aldol product. We're going to make this new carbon-carbon bond, and we're going to make that bond from this enolate and this aldehyde. And of course this enolate comes from that aldehyde. So in this case, if we just took this aldehyde and treated it with some relatively weak base like sodium ethoxide or sodium hydroxide, we should expect to get some of this aldol product. How about that one? This product is a dehydration product of an aldol, right? So here, this is lost water from this hydroxy ketone. Here, my new bond is going to be the one between that alpha carbon and the new alcohol. And if I kind of work backwards from there, I would end up with this enolate attacking that carbonyl, which brings me to a diketone like this, right? So this is a 1, 2, 3, 4, 5, 6, 7 carbon diketone. If I cook this up in acid or base, I should expect to get a fair amount of this final product. So far, we've only talked about when our nucleophile and electrophile come from the same carbonyl. But what if they don't? So here I've got two carbonyl compounds, and let's say I throw them in the same pot together with some base. Which one is going to be the electrophile, and which one's going to be the nucleophile? The answer is a lot of products. I've got 4 products right here, 4 different ways I can combine these things to give an aldol product, some with itself and some with another reactant there. These are called crossed aldols. But I've got very little control, and probably the major product is going to be this one because the aldehyde is easier to attack and is probably also easier to deprotonate. So I'm really not going to have the control I want over this. So I have to go back to basics. How can I get a crossed aldol? Let's say I wanted this product. How could I make it so that I can select which of these carbonyls is the nucleophile and which is the electrophile? Here's one solution. Cheat and pick better starting materials. So here, now I've got 2 carbonyls where I know which one's going to be my enolate and which one's going to be my nucleophile, because this can't form an enolate. There's no alpha proton with a nice acidic CH that I can take with a base. So I cannot form an enolate from this one. I can only form an enolate from this one. At the same time, this is a much better electrophile because the aldehyde is less hindered. So it's easier for me to attack this with some nucleophile. And here, that nucleophile is going to be this enolate. So here's my product. Again, it's an aldol product. It's symmetrical. It's not symmetrical. I know which one my enolate came from, which one was my electrophile. This one in particular is probably going to lose water because this alkene can be conjugated to both the benzene and that carbonyl over there. So again, if you can get away with using a non-enolizable aldehyde, that's the best aldol because now I don't have to worry about which one's my enolate and which one is getting attacked. If you can't change your starting materials, at least let's make sure we convert all of our ketone over to enolate. So if I use a really strong non-nucleophilic base like LDA, right? Here's an LDA with the antlers. It is too bulky to get in there and act as a nucleophile. So here I can take this ketone at low temperature, convert 100% of it over to enolate with this strong base. Now that I have 100% enolate, I don't have to worry about some of this remaining to be a electrophile. Right? It's all over here, so I can then add some electrophile ketone or aldehyde and get the aldol product that I want. So this is called a crossed aldol, and it works, but it only works if I can fully deprotonate my starting material here. And again, to complexify it further, you notice that I've been drawing symmetrical ketones, right? Sometimes I'll need to worry about how to deprotonate one side or the other, but we'll save that for another day. But for now, a good crossed aldol, which is to say two different carbonyl compounds reacting, works best if A, one of them can't form an enolate and the other one can, or B, we make sure to convert one of them entirely to enolate before we add the electrophile. Otherwise, if we just chuck in two carbonyl compounds and with some base, I can't tell which one's going to be my nucleophile and which one's going to be my electrophile.